Mechanical equilibrium. Objectives: mechanical equilibrium. Distinguish between force and net force. Describe the equilibrium rule and give examples. Distinguish between support, force, and weight. Give examples of moving objects that are in equilibrium, and determine the resultant of a pair of parallel or non-parallel vectors. The big idea. The object in mechanical equilibrium is stable without changes in motion. It's very good when your life is stable, when things important to you are in balance. It's also nice when the needs of family and friends are in harmony. Financially, we prefer our expenses to be balanced by earnings. Economists are concerned with the balance between the inflow and the outflow of goods. These examples illustrate the idea of equilibrium. In nature, we see an energy equilibrium when energy radiated away from Earth is balanced by the input of solar energy from the sun. Whenever a glass thermometer acquires the same temperature as the object being measured, we have thermal equilibrium. There are many forms of equilibrium. In this chapter, we will be concerned with mechanical equilibrium. Things in mechanical equilibrium are stable, without change in motion. The rocks shown at the right are in mechanical equilibrium. An unbalanced external force would be needed to change their resting states. You can see they're all very balanced. All the weight is evenly distributed very clearly. How do we know when an object is in equilibrium? 1. Stretch a strong rope between another student and yourself. 2. With the two of you pulling hard on the rope, have a third person push down on the center of the rope with his or her little finger. And 3. Try to make the rope straight while the person continues to push down on the center of the rope. Analyze and conclude. Did the rope remain straight when the application of a small downward force on the center of the rope? Predicting. Is there any way to make the rope straight as long as someone is pushing down on the center of the rope? And 3, making generalizations. What do you think are the conditions necessary for equilibrium? Consider these 3 very carefully. 2.1, force. A force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The state of motion may be one of rest or of moving uniformly along a straight line path. For example, a hockey puck at rest on ice remains at rest until a force is exerted on it. Once moving, a hockey puck sliding along the ice will continue sliding until a force slows it down. A force is needed to change an object's state of motion. Net force. Most often, more than one force acts on an object. The combination of all forces acting on an object is called the net force. The net force of an object changes its motion. For example, suppose you pull horizontally on an object with a force of 10 pounds. If a friend assists you and also pulls in the same direction with a force of 5 pounds, then the net force is the sum of these two forces, or 15 pounds. The object moves as if it were pulled with a single 15-pound force. However, if your friend pulls with a force of 5 pounds in the opposite direction, then the net force is the difference of these forces, or 5 pounds towards you. The resulting motion of the object is the same as if it were pulled with a single 5-pound force. This is shown in figure 2.1, where instead of pounds, the scientific use of force is used, the Newton, abbreviated capital N. Applied force, so you have 5 newtons and 10 newtons in the same direction, that's 15, and so on. And on the right is the net force, and it's not only the magnitude, 15, 5, and 0, but it's also the direction that is also important. That's why they are vectors, magnitude and direction. When you hold a rock at rest in your hand, you are pushing upward on it with as much force as Earth's gravity pulls down on it. If you push harder, it will move upward. If you push with less force, it will move downward. But just holding it at rest, as shown in figure 2.2, means the upward and the downward forces on it add to 0. The net force on the rock, or in this case, the Earth, the globe, is 0. So the upward is the support force, or the normal, and the downward is the weight. Fn for normal, Fw for weight. And this is classic for all forces, for weight. When you're weightless, you actually are missing the support force. The weight is still there, but the support force is not, or the upward Fn. Tension and weight. If you tie a string around a 2-pound bag of sugar and suspend it from a scale, a spring in the scale stretches until the scale reaches 2 pounds, as shown in figure 2.3. The stretched spring is under a stretching force called tension. A scale in a science lab is likely calibrated to read this 2 pounds force as 9 newtons. Both pounds and newtons are units of weight, which in turn are units of force. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds, or equivalently 9 newtons. Suspend twice as much sugar from the scale, and the reading will be 18 newtons. There are 2 forces acting on the bag of sugar: tension force acting upward, and weight acting downward. 2.3a, the upward tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is 0. B shows a 2-pound bag producing a tension of 9 newtons. The weight is actually slightly more than 2 pounds, and the tension is slightly more than 9 newtons. Consider this figure very, very carefully. The 2 forces on the bag are equal and opposite, and they cancel to 0. The net force on the bag is 0, and it remains at rest. Force vectors. In figures 2.1 and 2.2, forces are represented by arrows. When the length of the arrow is scaled to represent the amount, magnitude of the force, and the direction of the arrow points in the direction of the force, we refer to the arrow as a vector. A vector is an arrow that represents the magnitude and direction of a quantity. A vector quantity is a quantity that needs both magnitude and direction for a complete description. Force is an example of a vector quantity. Figure 2.4, this vector scaled so that 1 centimeter equals 20 newtons represents a force of 60 newtons to the right. That arrow is not 3 centimeters, but we're pretending it is, and therefore it would be 60 newtons. Here is another shot of figure 2.1. The net force depends on the magnitudes and direction of the applied forces. Consider this very carefully. And here is another shot of figure 2.2 when the girl holds the rock with as much force upward as gravity pulls downward. The net force on the rock is 0. By contrast, a scalar quantity is a quantity that can be described by magnitude only and has no direction. Time, area, volume are scalar quantities. Speed as well. We'll return to vectors in Chapter 5. Scalars can be added, subtracted, multiplied, and divided like ordinary numbers. When 2 liters of water are added to 3 liters of water, the result is 5 liters. But when someone is pulled by 2 forces, one 2 newtons and the other 3 newtons, the result may or may not be 5 newtons. Vector quantities, direction matters. How can you change an object's state of motion? By applying an external force. Essay by the author, Paul Hewitt, an excellent teacher. This is an essay written by Paul Hewitt, and it is included in his wonderful text, Conceptual Physics. When I was in high school, my counselor advised me not to enroll in science and math classes, but to instead focus on what seemed to be my gift for art. I took his advice. I was then interested in drawing comic strips and in boxing, neither of which earned me much success. After a stint in the U.S. Army, I tried my luck at sign painting, and the cold Boston winters drove me south to Miami, Florida. There, at age 26, I got a job painting billboards and met a new friend, Burl Gray, a sign painter with an active intellect. Burl, like me, had never studied physics in high school, but he was passionate about science in general. He shared that passion with me by asking many fascinating science questions as we painted together. I remember Burl asking me questions about the tensions in the ropes that held up the scaffold we stood on. The scaffold was simply a heavy horizontal plank suspended by a pair of ropes at each end. Burl twanged the rope nearest to his end of the scaffold and asked me to do the same with mine. He was comparing the tensions in the 2 ropes to determine which was greater. Burl was heavier than I was, and he guessed that the tension in the rope was greater, like a more tightly stretched guitar string. The rope with greater tension twanged at a higher pitch. That Burl's rope had a higher pitch seemed reasonable because his rope supported more of the load. When I walked towards Burl to borrow one of his brushes, he asked me if tensions in the rope had changed. The tension in his rope increased as I moved closer. We agreed that it should have, because even more of the load was then suspended by Burl's rope. How about my rope? Would its tension decrease? We agreed that it would, for it would be supporting less of the total load. I was unaware at the time that we were discussing physics. Burl and I used exaggeration to bolster our reasoning, just as physicists do. If we both stood at an extreme end of the scaffold and leaned out, it was easy to imagine the opposite end of the staging rising like the end of a seesaw with the opposite rope going limp. Then there would be no tension in that rope. We then reasoned the tension in my rope would gradually decrease as I walked towards Burl. It was fun posing such questions and seeing if we could answer them. A question that we couldn't answer was whether or not the decrease of tension in my rope when I walked away from it would be exactly compensated by a tension increase in Burl's rope. For example, if the tension in my rope underwent a decrease of 50 newtons, would Burl's rope gain 50 newtons? We talked pounds back then, but here we use the scientific unit of force, the Newton, abbreviated capital N. Would the gain be exactly 50 newtons? Or if so, would this be a grand coincidence? I didn't know the answers until more than a year later when Burl's simulation resulted in my leaving full-time painting and going to college to learn more about science. At college, I learned that any object at rest, such as the sign painting scaffold that supported us, experiences no net force. It is said to be in equilibrium. That is, all the forces that act on it balance to zero. Sigma F equals zero. So the sum of the upward forces supplied by the supporting ropes do indeed add up to the downward forces of our weights plus the weight of the scaffold. A 50 Newton loss in one would be accompanied by a 50 Newton gain in the other. I tell this story, this true story, to make the point that one's thinking is very different when there is a rule to guide it. Now, when I look at any motionless object, I know immediately that all the forces acting on it cancel out. We view nature differently when we know its rules. It makes nature seem simpler and easier to understand. Without the rules of physics, we tend to be superstitious and see magic where there is none. Quite wonderfully, everything is beautifully connected to everything else by a surprisingly small number of rules. The rules of nature are what the study of physics is all about. 2.2 Mechanical Equilibrium. Mechanical equilibrium is a state wherein no physical changes occur. It is a state of steadiness. Whenever the net force on an object is zero, the object is said to be in mechanical equilibrium. This is known as the equilibrium rule. You can express the equilibrium rule mathematically as sigma F equals zero. The symbol sigma stands for the sum of, and F stands for the forces. Please don't be intimidated by the expression sigma F equals zero, which is physics shorthand that says a lot in so little space. That all the forces acting on something add vectorially to zero. For a suspended object at rest, like the bag of sugar mentioned earlier, the rule states that forces acting upward on the object must be balanced by other forces acting downward to make the vector sum equal zero. Vector quantities take direction into account. So if upward forces are positive, downward ones are negative, and when summed, they equal zero. If you look carefully at bridges and other structures around you, you'll see evidence of sigma F equal zero. Consider the gymnast above hanging from the rings. If she hangs with her weight evenly divided between the two rings, how would scale readings in both supporting ropes compare with her weight? Suppose she hangs with slightly more of her weight supported by the left ring. How would a scale on the right read? In the first case, the reading on each scale will be half her weight. In the second case, when more of her weight is supported by the left ring, the reading on the right reduces to less than half her weight. But In both cases, the sum of the scale readings equal her weight. In figure 2.5, we see the forces of interest to Burl and Paul on their sign painting scaffold. The sum of the upward tensions is equal to the sum of their weights plus the weight of the scaffold. Note how the magnitudes of the two upward vectors equal the magnitudes of the three downward vectors. Net force on the scaffold is 0, so we say it is in mechanical equilibrium. How can you express the equilibrium rule mathematically? Sigma F equals 0, or F net equals 0. Figure 2.5 shows quite clearly the sum of the upward vectors equals the sum of the downward vectors. Sigma F equals 0, and the scaffold is in equilibrium. Support force 2.3. Consider a book lying at rest on a table as shown in figure 2.6a. The book is in equilibrium. What forces act on the book? One is the force due to gravity, the weight of the book. Since the book is in equilibrium, there must be another force acting on it to produce a net force of 0, an upward force opposite to the force of gravity. Where is the upward force coming from? It is coming from the table that supports the book. We call this the support force, or the normal force you can see in other books. The upward force that balances the weight of the object on a surface. A support force is often called the normal force. 2.6, the table pushes up on the book with as much force as the downward weight of the book. B, the spring pushes up on your hand with as much force as you push down on the spring. Consider this drawing very carefully. The support force and the weight, or simply the downward force and the upward force. We'll see this in many, many different ways in the next few chapters, and we'll illustrate, such as Newton's third law, equal and opposite reaction, just to name one example. For an object at rest on a horizontal surface, the support force must equal the object's weight. So in this case, the support force must equal the weight of the book. We say the upward force, or the upward support force, is positive and the downward weight is negative. The two forces add mathematically to 0. So the net force on the book is 0. Another way to say the same thing is sigma F equals 0. To better understand that the table pushes up on the book, compare the case of the compressing spring, shown in figure 2.6b. If you push the spring down, you can feel the spring pushing up on your hand. Similarly, the book lying on the table compresses atoms on the table, which behave like microscopic springs. And here is another view of figure 2.6a and b, the book and the spring. Notice the downward force and the upward force. The weight of the book squeezes downward on the atoms, and they squeeze upward on the book. The compressed atoms produce the support force. When you step on a bathroom scale, two forces act on the scale, as shown in figure 2.7. One force is a downward pull of gravity, your weight, and the other is the upward support force of the floor. These forces compress a mechanism, in effect a spring, that is calibrated to show your weight. So the scale shows the support force when you're standing on a bathroom scale at rest. The support force and your weight have the same magnitude. 2.7, the upward support force is as much as the downward pull of gravity, Fw and Fn. Concept check. For an object at rest on a horizontal surface, what is the support force equal to? The weight. Think. What is the net force on the bathroom scale when a 110-pound person stands on it? 0. As the scale is at rest, the scale reads the support force, which has the same magnitude as the weight, not the net force. Think. Suppose you stand on 2 bathroom scales with your weight evenly distributed between the 2 scales. What is the reading on each of the scales? What happens when you stand with more of your weight on one foot than the other? In the first case, the reading on each scale is half your weight. The sum of the scale reading balances your weight, and the net force on you is 0. In the second case, if you lean more on one scale than the other, more than half your weight will be read on that scale, but less than half on the other. In this way, they add up to your weight. 2.4 Equilibrium for moving objects. When an object isn't moving, it's in equilibrium. The forces on it add up to 0, but the state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also in a state of equilibrium. Once in motion, if there is no net force to change the state of motion, it's in equilibrium. Equilibrium is a state of no change. A hockey puck sliding along slippery ice or a bowling ball rolling at constant velocity is in equilibrium until either experiences a non-zero net force, whether at rest or steadily moving in a straight line path. The sum of the forces on both is 0. Sigma F equals 0. Interestingly, an object under the influence of only one force cannot be in equilibrium. Net force is, in that case, is not 0. Only when there is no force at all, or when two or more forces combine to 0, can an object be in equilibrium. We can test whether or not something is in equilibrium by noting whether or not it undergoes changes in motion. Figure 2.8 shows a desk being pushed horizontally across a factory floor. If the desk moves steadily at a constant speed without change in motion, it is in equilibrium. This tells us that more than one horizontal force acts on the desk, likely the force of friction between the bottom of the desk and the floor. Friction is a constant force between objects that slide or tend to slide against each other. More about friction in Chapter 6. The fact that the net force on the desk equals 0 means that the force of friction must be equal to the magnitude and opposite in direction to our pushing force. So it is in mechanical equilibrium. Let's look at the figure. When the push of the desk is as much as the force of friction between the desk and the floor, the net force is 0 and the desk slides at an unchanging speed, or in mechanical equilibrium. Notes. Types of equilibrium include static at rest and dynamic, moving at a constant speed in a straight line path. Objects at rest are said to be in static equilibrium. Objects moving at a constant speed in a straight line path are said to be in dynamic equilibrium. Both of these situations are examples of mechanical equilibrium. As mentioned at the beginning of the chapter, there are other types of equilibrium. In Chapter 11, we'll discuss another type of mechanical equilibrium. rotational equilibrium. Then, in Chapter 21, when we study heat, we'll discuss thermal equilibrium, where temperature doesn't change. Think. An airplane flies horizontally at a constant speed in a straight line direction. Its state of motion is unchanging. In other words, it is in equilibrium. Two horizontal forces act on the plane. One is the thrust of the propeller that pulls it forward. The other is the force of air resistance, air friction, that acts in the opposite direction. Which force is greater? Let's see. Neither, for both forces have the same strength. Call the thrust positive and the air resistance negative. Since the plane is in equilibrium, constant velocity, constant speed, the two forces combine to equal zero. The equilibrium rule, sigma F equals 0, provides a reasoned way to view all things at rest: balanced rocks, objects in your room, or the steel beams in bridges. Whatever their configuration, if at rest, all acting forces always balance to 0. The same is true of objects that move steadily, not speeding up, slowing down, or changing direction. For such moving things, all acting forces also act to 0. The equilibrium rule is one that allows you to see more than meets the eye of the casual observer. It's good to know the rule of the stability of things in our everyday world. Physics is everywhere. How are static and dynamic equilibrium different? 2.5, vectors. Look at figure 2.9. When gymnast Nellie Newton is suspended by a single vertical strand of rope, figure 2.9a, the tension in the rope is 300 newtons, her weight. If she hangs by two vertical strands of rope, figure 2.9b, the tension in each is 150 newtons, half her weight. Rope tensions pull her upward and gravity pulls her downward. In the figures, we see that the vectors representing rope tensions and weight balance out. Sigma F equals 0, and she is in equilibrium. Combining vectors is quite simply when they are parallel. If they are in the same direction, they add. If they are in opposite directions, they subtract. The sum of two or more vectors is called their resultants. It's a new word, resultant, very important. 2.9a, the tension in the rope is 300 newtons, equal to Nellie's weight. B, the tension in each rope is now 150, half of Nellie's weight. In each case, sigma F equals 0. But what about vectors that act at an angle to each other? Consider Nellie hanging by a pair of ropes shown in figure 2.10. To find the resultant of non-parallel vectors, we use the parallelogram rule. The parallelogram rule defines the resultant of two non-parallel vectors. Construct a parallelogram wherein the two vectors are adjacent sides. The diagonal of the parallelogram shows the resultant. Look to the parallelogram. Consider two vectors at right angles to each other as shown below. The constructed parallelogram in this special case is a rectangle. The diagonal is the resultant R. In the special case of two perpendicular vectors that are equal to magnitude, the parallelogram is a square. Since for any square the length of the diagonal is root 2, or 1.414, times one of the sides, the resultant is root 2 times one of the vectors. For example, the resultant of two equal vectors of magnitude 100 acting at right angles to each other is 141.4. Now consider the vectors shown below, which represent the tensions of the rope on figure 2.10. Notice that the tension vectors form a parallelogram in which the resultant R is vertical. The plot thickens, as they say when the plot's about to thicken. When the ropes are at an angle to each other, you need to use the parallelogram rule to determine their tension. Applying the parallelogram rule. When Nellie Newton is suspended at rest from the two non-vertical ropes shown in figure 2.10, is the rope tension greater or less than the tension in the vertical ropes? Note there are three forces acting on Nellie: a tension in the left rope, a tension in the right rope, and her weight. Figure 2.11 shows a step-by-step solution. Because Nellie is suspended in equilibrium, the resultant of the rope tensions must have the same magnitude as her weight. Use the parallelogram rule, we find the tension in each rope is more than half her weight. In figure 2.12, the ropes are at a greater angle from the vertical. Note that the tensions in both ropes are appreciably greater. All right, here's A. Nellie's weight is shown by the vector, the downward vertical vector. An equal and opposite vector is needed for equilibrium, shown by the dashed vector. B, the dashed vector is the diagonal of the parallelogram defined by the dotted lines. Very curious. And then C, both rope tensions are shown by the constructed vectors. Figure 2.12, as the angle between the ropes increases, tension increases, so that the resultant dashed line vector remains at 300 newtons upward, which is required to support 300 Newton Nellie. As the angle between the supporting ropes increases, the tension increases. In terms of the parallelogram, as the angle increases, the vector lengths increase in order for the diagonal to remain the same. Remember, the upward diagonal must be equal and opposite to Nellie's weight. If it isn't, she won't be in equilibrium. By measuring the vectors, you'll see that for this particular angle, the tension in each rope is twice her weight. In figure 2.13, we see Nellie hanging by ropes at different angles from the vertical. Which rope has the greater tension? By the parallelogram rule, we see that the right rope bears most of the load and has the greater tension. If you understand this physics, you will understand why a vertical clothesline can support your weight while a horizontal clothesline cannot. Figure 2.13, here's the rope supporting Nellie have different angles. Note that tension is unequal in the two ropes. The tension in the horizontal clothesline is much greater than the tension in the vertical clothesline. And so the horizontal one breaks. How can you find the resultant of two vectors? Figure 2.14, you can safely hang from a clothesline hanging vertically, but you'll break the clothesline if it is strung horizontally. Two sets of swings are shown below. If the children on the swings are of equal weights, the ropes of which swing are more likely to break? The tension is greater in the ropes hanging at an angle. The angled ropes are more likely to break than the vertical ropes. Consider what would happen if you suspend a 10 Newton object midway along a very tight, horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? No way. If the 10 Newton load is to hang in equilibrium, there must be a supporting 10 Newton upward resultant. The tension in each half of the guitar string must form a parallelogram with a vertically upward 10 Newton resultant. For a slight sag, the sides of the parallelogram are very, very long, and the tension force is very large. To approach no sag is to approach an infinite tension. Summary: mechanical equilibrium. A force is needed to change an object's state of motion. You can express the equilibrium rule mathematically as sigma F equals 0. For an object at rest on a horizontal surface, the support force must equal the object's weight. Objects at rest are said to be in static equilibrium. Objects moving at constant speed in a straight line path are said to be in dynamic equilibrium. To find the resultant of two non-parallel vectors, construct a parallelogram wherein the two vectors are adjacent sides. The diagonal of the parallelogram shows the resultant.